Hi everybody. So today what I want to talk to you about is what we did in class. And in the last video, I actually had asked you to set up what this would look like in terms of an ice table. And this is what we did in class together, and this is kind of a review, but just a chance for you to look at this at your own pace in case we went too quickly. So we set up the reaction in an ice table as shown down at the bottom here. And then we put in the concentrations that we started with. And then we put in the terms minus x for the N2, minus x for the O2, plus 2x because the coefficient of NO is 2. And then we went through for the equilibrium and did the initial plus the change and got 0.2 minus x for N2, 0.15 minus x for O2, and 2x for NO. What we then did was we wrote out a KEQ and plugged in the values for x. Now at this point, we have our x's here and we can't do the square root because there's no perfect square. So when we set this up, we would FOIL out the denominator and cross multiply. And when we did that, we would get this set up here. And then shown in purple highlight is the quadratic equation that we set up. Now if we solve for x using the quadratic formula, we will get x equals 0.0018. And then we could plug this back in and we can solve for our concentrations of our three substances in equilibrium. Now the thing is this, is that, although this is the way to do it, you could use a quadratic, we could actually take some liberties here and we could simplify this equation. And that's also what I showed you in class too. And what I showed you in class was that the K value is very small, 4.1 times 10 to the negative fourth. And that because of this, the X value, and we can see that in our result, look at how tiny X is here that I'm underlining. X is really, really small compared to the initial values. So we can neglect X. And when we do that, we get this simplified version of the equation that I just drew an arrow pointing to in pink. And we have, instead of 0.2 minus x, we just have 0.2. Instead of 0.15 minus x, we just have 0.15. And if we solve for the x on top here, and we go through and we take the square root, look at what our x value is. Our x value is 0.0018. And what then proceeded in class was this discussion of, well, how do you know that you can neglect x? And the idea is that when k is very, very small, like 10 to the negative 4 small, the change, the amount of reactant forming product is also very, very small. Remember, when you have a small k, you don't form a lot of products. So we can neglect that x because the change is really, really tiny. My advice to you is, if you see that you're going to have to do a quadratic and your k is a small value, start by neglecting x right in the beginning. So do the problem by neglecting x, and then test using something called the 5% rule. What is the 5% rule? Well, it's stated down here. It says that when the equilibrium constant is really small, and I change that to 10 to the negative 4 instead of 10 to the negative 5, it means that you're going to have less than 5% of the reactants forming into products. And now we can cancel out that minus x term. So let's test this out, and I did this in class again. Let's test out our 0.0018 against our reactants. So when we test this out, we put in the concentration of our X value over the concentration of the initial NO value. That's all the way back from here, where we had the NO value is 0.15. We times it by 100 to get percent, and we see that we have about 1.2% that's associated. So then I gave you this problem to try in class, where we can try this problem in class in which we have HF reacting to form H plus and F minus. And I ask you what the concentrations of HF, F minus, and H plus are at equilibrium, given that you have 0.2 molar HF reacting. And I give you the KEQ for this. And so we set up our ice table again. And now we can see that our K value is very, very small, so we're going to go ahead and we're going to neglect X on the bottom. We're going to solve for x, and we get that x is equal to 2 times 10 to the negative third. Well, let's go through and test to see if this matches and works with our 5% rule. So if we use our 5% rule, we have the value of x over the initial, so 0.002 is our x value, over the initial, which is 0.2, times 100, and we get 1%. So there we have our, 1%, and we can see that it's less than 5%. So I just wanted to spend this time going through this video, revisiting what we did in class today. Normally you see the videos first, but here we did some of this in class, and I want you to have the video to refer to, so that if you want to go back and look at this again, you can, along with my notes on the topic. Alright, thanks so much for watching. Actually, you know what? Let's really quickly manipulate k, so that next time we can do k cubed. So let me just show you really quickly what I mean by manipulating k. Let's say that we had our equation like 2hi, and it forms h2 plus i2. And I give you a k for that. Let's say I say the k is 10. Well, what if I were to write the reverse? So I were to write h2 plus i2, and you form 2hi. So what happens to the k is, because the new k expression is going to be 1 over the original, the reactants are now products, the products are now reactants, we're going to have 1 over k, and our value is going to be 110. Likewise, if we were to take this 2hi and make it 4hi, and have that yield 2h2 plus 2i2, now all the coefficients are doubled. And remember, we're using the coefficients as exponents. And so this would become 10 squared, or 100. It's different from Hess's law, where with Hess's law, when you reverse the equation, you did negative, and when you doubled the equation, you doubled the delta h. Here, because everything's multiplication and exponents, we, do the reciprocal, or we square it. So those are the effects on k when you manipulate equations. One last thing is, if I were to have a reaction like this, and then I were to have C goes to D, and I were to give you a k for this equals 10, and a k for this equals 5, and I were to ask you, well, what's the k for this one? A plus B goes to D. Remember, with Hess's law, again, we would add the two values together for delta H, but here is equilibrium. So instead of adding, we multiply. And so this would be 10 times 5, or 50. We'll practice some of these in class, but this is, like a general way to look at k values. All right, so next time we'll do Le Chatelier's principle. Thanks so much for watching. Really, seriously, this is it. And see you soon.